Welcome to a presentation on Neoclassical physics. Neophysics has the most accurate theories of physics. We challenge you to disprove us. If not, we welcome you to join us and profit from the new science. In this presentation, we discuss about extending classical type orbits to explain characteristics of hydrogen molecule. In the previous part, we discussed about how two protons can form a circular orbit in spite of repulsion, provided there is angular velocity conservation. The angular velocity conservation is associated with an attractive force, which can balance the repulsion. Using this idea, we can explain the three fundamental reactions involving hydrogen. 1. Dissociation of hydrogen molecular ion, that is the reaction H2+, which is the hydrogen molecular ion, plus 2.8 electron volts gives rise to H, the hydrogen atom, plus a proton, H+, or the hydrogen nucleus. This is the first reaction. Second, ionization of hydrogen molecule, that is the reaction H2, which is the hydrogen molecule, plus 15.4 electron volts gives rise to H2+, the molecular ion, plus a free electron. And the third reaction, dissociation of hydrogen molecule, that is the reaction H2 plus 4.74 electron volts gives rise to H plus H, that is two hydrogen atoms. In the previous part, we saw how two protons can form a stable circular orbit provided there is angular velocity conservation. If the separation distance between the two protons is 2r and their angular velocity is omega, then we get this circular orbit criteria, that is 4m r cube omega square equals q, where q is a constant which is equal to e square by 4 pi epsilon naught, where e is the charge on the protons and epsilon naught is the permittivity of free space. Here m is the mass of these protons. We used this idea to capture trends in the diatomic bond lengths in the previous video. In this presentation, we will make use of the concept of this attractive force in order to derive the ionization and dissociation energies of hydrogen molecular ion and hydrogen molecule. Suppose we introduce an electron, shown in this blue circle here, an electron in the vicinity of the proton group, that is H2+. This proton group has been shown as H2 because it has two positive charges, and we put an electron in its vicinity. So we have this three particle diagram here. Intuitively, according to the understanding built from electrostatics, we can assume that the electron could form stable orbits in the plane perpendicular to the line joining the two protons in H2+. So here we see a snapshot of the H2+ ion, that is the hydrogen molecular ion. It has three particles, proton, proton, electron, and we are showing the interaction here. If we assume the x, y, z coordinates here, this is x, this is y, this is z, and this O is the origin. If we assume the xyz coordinate is stationary, then in this instant shown here, the electron is going around in the xy plane, revolving around z axis. The electron is in fact revolving in the shaded plane perpendicular to the line joining the two protons. In the longer or the slower time scale, the axis of the proton itself rotates in the xz plane around y-axis. So the proton right now is shown oriented along the z-axis. This itself rotates in the xz plane around the y-axis. and the shaded plane also rotates around the y-axis attached to the axis of the proton. So this shaded plane is attached to this line joining the two protons. It's going right through the middle of this line and perpendicular to it, and it's attached to it. It rotates along with it. So the net energy of the system, this three particle system, ignoring the kinetic energy of the protons, is shown here. That is E equals Q by 2R plus half me dx by dt square plus half a square by mex square minus 2q by square root of r square plus x square. So this equation is the conventional strategy used, for example, in quantum mechanics. That is only considering the potential energy of the protons, this Q by 2R term here. And rest of the terms belong to the electron. Half me is the mass of the electron, x is the radial distance of the electron from the center of the system, center of mass, a is the angular momentum of the electron, and q is the constant we discussed earlier. So, and r is the distance of the radial distance of the proton from the center of mass. So these three terms belong to the electron, and Q by 2R is the potential energy term of the proton. So that has been, the potential energy term has been added to the electron energy terms. So assuming that the protons are at rest and kept at a fixed distance by some unknown force. So that is the assumption used here in this convention. So as usual, we consider the partial derivatives of E. So if E is constant, the energy, then we get that the partial derivative of E with respect to x, del E by del x, and the partial derivative of E with respect to r, del E by del r, they will be 0 because E is constant. Further, assuming the acceleration terms related with x and r as 0, that is d square x by dt square equals 0 and d square r by dt square equals 0, we get these equations. So basically here we are assuming that the radial distances x and r are constants. So that's why we take the acceleration term as 0, that is d square x by dt square is 0 and d square r by dt square equals 0. So that we get constant x and r solutions. So from the partial derivative of E with respect to x, we get this equation: a square by mex cube equals 2qx by r square plus x square power 3 by 2. And from the partial derivative of E with respect to r, we get this equation: q by 2r square equals 2qr divided by r square plus x square power 3 by 2. So when the angular momentum of the electron is h bar, a equals h bar is the lowest allowed angular momentum that the electron can have. So when a equals h bar, we get these values. 2r equals 1.732 rb, that is the separation length 2r between the two protons, becomes 1.732 into rb, and x, which is the radial distance of the electron, becomes 1.067 rb. Here rb is nothing but h bar square by qme, which is the radius of Bohr's first orbit, or the which is the radius of the first orbit in the hydrogen of the electron in the hydrogen atom, or the radius of Bohr orbit. So we scale all our distances with respect to rb. So we represent 2r, that is the distance between the two protons, as this 1.732 rb, and the radial distance of the electron as 1.067 rb. So we get these x and r values from the partial derivative of E. Now using these r and x values in the energy equation and ignoring the dx by dt term because x is constant, we get this equation. So q by 2r term remains the same. a square by me x square, this term becomes q by 4r 1.233 square, and this term becomes this last potential energy term becomes this. So overall the energy, this adds up to minus 11.94 electron volt. So this equation demonstrates the lowest possible energy state of this energy equation, or the configuration shown here, the three body configuration shown here. The lowest energy state of that is minus 11.94 electron volt. We can also numerically verify it following the method shown here next. So when a, the angular momentum, is h bar, the partial derivative of E with respect to x, del E by del x, gives this equation, which can be rearranged to get this equation, which basically implies that x equals rb by 2 into 1 plus r square by x square whole 3 by 2. So x can be purely expressed in terms of this ratio r by x and a constant rb. So assuming various r by x ratios, we can calculate the different x values from this equation. And using the equation r equals r by x into x, because we know x from this equation and r by x is assumed, we can find the value of r corresponding to this r by x by just multiplying the x corresponding to that r by x from this equation. So we get r. So thus we get x and r uniquely for any given value of r by x, the ratio r by x. So using x and r values in the energy equation and ignoring the dx by dt term, we get the different ionization potential or the binding energy of the electron. We can compile a table of these values and verify the minimum energy state, that is minus 11.94 electron volt. So using this energy equation, we can define a couple of new terms, that is E electron, that is the energy of the electron, has these two terms shown here, half a square by me x square minus 2q by r square root of r square x plus x square, and we define another term E bind, or the binding energy, which is nothing but the sum of the potential energy of the protons q by 2r and the energy of the electron E electron. So here it is E bind and here it is the E electron. So, and from the previous slide we saw how to determine x and r given a ratio r by x. So at various values we compile this table using these definitions E electron, E bind, x and r here. So we get this table. So as we can see, the minimum energy, minimum binding energy in this table is minus 11.94 electron volts, as we saw in the previous slide. And 2r, which is the separation distance between the protons, is 1.732 rb and x is 1.067 rb, just as we saw in the previous analysis. Here we get this minimum value from a different method, but we get the same values. But it has been experimentally observed that we need minus 16.4 electron volts to ionize or dissociate H2+. Here we have got just 11.94. Actually, instead of 11.94, it should be 16.4. That is according to the experiment. We observe that what is called a Coulomb explosion. Coulomb explosion when we ionize H2+. The protons carry away a kinetic energy of about 1 to 5 electron volts in these explosions, as we discussed in the previous part of the video. So this is how we visualize the Coulomb explosion. This is the circular orbit in which the protons were present. So the rotational energy of this is half m r square omega square, which is equal to q by 8r, where r is the separation length between these two protons. And so whenever the Coulomb explosion happens, basically this rotational energy term is converted to linear kinetic energy term and is carried away along with the protons. The protons basically break from this circular orbit and go along a straight line, carrying the rotational energy term. So rather than explosion, they could be like disengagement of the circular motion, like snapping of a string maintaining a circular motion in hammer throw. The analysis, ignoring the proton kinetic energy, predicts only 11.94 electron volts. It cannot explain the experimental dissociation energy of 16.4 electron volts, and also it cannot explain the origin of the kinetic energy of protons in the Coulomb explosion, especially since the proton's potential energy is added to the electron. So basically this Q by 2R is the proton's potential energy, and these terms inside this blue square are the terms associated with the electron's energy. The proton's potential energy is added to the electron's energy to define the binding energy in the previous case. Since we are adding this Q by 2R to this electron energy term, the leftover terms there are no leftover terms, so we cannot explain the kinetic energy carried by the protons in the Coulomb explosion. However, the whole equation corresponding to this three particle system will be something like this. These terms, crossed out terms here, are the kinetic energy terms of the proton. Half mp dr by dt square, which is the radial kinetic energy term, and half mp r square omega square, which is the angular or the rotational kinetic energy term of the proton. This had been ignored in the previous analysis. So let us now incorporate the kinetic energy terms of the protons, that is these terms, crossed out terms. Let us now try to include those terms in our analysis. And let us assume that the linear kinetic energy observed in the Coulomb explosion of protons is just a transformation of this rotational energy that they possess, this rotational energy that we show in this figure. So this rotational energy is converted to linear kinetic energy, and we call that the Coulomb explosion. So this whole equation represents the net energy of the three particle system. So this term is the proton energy, and this is the electron energy, and this is the potential energy of the proton. So we will also have a rotational energy term associated with the angular velocity big omega of the electrons. That is because the plane of revolution of the electron itself is rotating with this angular velocity big omega. The electron will also have a rotational energy term because of that. If x is of the order of Rb, Bohr radius, and omega is of the order of omega b by 100, that we saw in the case of the hydrogen atom in the previous video, we estimated that the big omega must be of the order of omega b, the small omega b, which is the angular velocity of the Bohr orbit, first Bohr orbit. So the big omega is of the order of omega b by 100. So therefore we get that the kinetic energy associated with this electronic angular velocity with big omega is me x square omega square is much lesser than the energy due to this angular momentum term a square by me x square, which is much lesser. And this me x square omega square is also much lesser than the mp r square omega square term of the proton. So we can drop this term me x square omega square from the energy equation. So we have not used it here because it is insignificant. So further, considering the partial derivatives of this energy equation, del E by del x equals 0 and del E by del r equals 0, and then further considering the radial distance terms, d square x by dt square equals 0 and d square r by dt square equals 0, we get these following expressions for the constant values of r and x. The relationship between r and x, where r and x are constant values or constant radial distances. So x turns out to be rb by 2 into 1 plus r square by x square power 3 by 2, as we saw in the previous. This is the same expression, and this is the same r we get by multiplying x with r by x, and this is a new term which shows the value of mp omega square, or which shows the relationship between omega, r and x. So if we compile a table of values using this x, r and omega square expressions, we get this. So at different r by x values, different ratios, like for example 0.6, 0.7, these are the different values we get. So from this table we see that it does not have a well-defined minima as such, but it has a limiting case. In the limiting case, when the ratio r by x tends to 0.811, the net energy shown as pp, that is the proton, proton, electron, this three particle system, the net energy in the table shows minus 11.94 electron volt. This becomes minus 11.94, which is same as the value we saw earlier. This happens because omega becomes 0 in that case. So we can see this mp omega square is quite low, 0.2. So at the limit, in the limiting case, this becomes 0. Mp omega square becomes 0. So it is as good as this term here in this expression is not there, which is the same as the last same equation that we used in the previous analysis. So we get the same minimum energy state, minus 11.94. But otherwise it doesn't have a well-defined minima. There is no this is not a minima, this is an edge case. In order to get realistic estimates of the binding energy, we may need to consider the kinetic energy carried away by the protons during the Coulomb explosion. We need to account for it when we supply energy to ionize or dissociate the hydrogen system. So this is the net energy we saw earlier of the three particle system. This portion we name it as EPP, or the energy of the proton-proton system. There are two protons. And this we call as the energy of the electron, ELEC. And in this equation there is an omega, big omega terms, and associated with this big omega we can define a relaxed length. That is the length, the separation length between the protons in the absence of electrons, but the protons will be having this angular velocity omega. So when the protons have this angular velocity omega in the absence of electrons, they will achieve a certain separation length. We call that as the relaxed length, because there are no electrons affecting the system. So the relaxed length corresponding to this big omega can be obtained from the circular orbit criteria shown here. So this is in the absence of electrons. The rotational energy of the protons in the circular orbit corresponding to this relaxed length R0 is Q by 4 R0, shown here. This is the kinetic energy of the electrons corresponding to the relaxed length. And we negate this Q by 4 R0, that is the kinetic energy, from the net energy term. So this PPE is nothing but EPP, the energy of the proton-proton system, plus the energy of the electron. So this is basically the net energy of the system, E or PPE, which is written as the net energy of the three particle system, proton, proton, electron, is shown as PPE here. And PP is, we negate Q by 4 R0, which is the kinetic energy term of the protons associated with the relaxed length R0. We negate that term from the total energy. Because this is carried away by the protons during dissociation. So we assume that when we completely ionize the hydrogen molecular ion to bare protons, the protons move away carrying the rotational energy corresponding to the circular orbit that they would achieve in the absence of electrons. That is the circular orbit with the relaxed length 2 r naught. The potential energy term q by 2 r naught. This q by 4 r naught is the kinetic energy term of the two protons, and q by 2 r naught is the potential energy term between them. The potential energy of this orbit, this circular orbit with relaxed length, this energy remains with the electrons. The potential energy remains with the electron, the kinetic energy is carried away by the protons. So, and we call this as the electronic binding energy term, the electron binding energy term. So the electron binding energy term is nothing but the total energy of the three particle system minus the kinetic energy of the proton, q by 4 r naught. Now let us numerically calculate the binding energy at various r by x ratios. The expressions relating x, r and m omega square stay as it is, as we saw in the previous slide. Only we need to minimize the binding energy term now. So this is x we saw earlier, this is how we get r we saw earlier, and this is the equation for mp omega square for calculating omega given r and x, or for relating r, x and omega. And this is for a given omega, this is how we calculate the relaxed length, and this is the binding energy term we defined in the previous slide. So it is nothing but the total energy of the three particle system, ppe, minus q by 4 r naught. So tabulating the E bind or the binding energy and other parameters at different r by x values, we get this table. So from this table we can see that this minus 15.4 electron volt is the minimum possible binding energy or the minimum possible E bind. And ppe equals minus 9.6 electron volts. So ppe is the total energy of the three particle proton-proton electron system. So here it is even higher than the pp equals minus 11.94 electron volt we found by ignoring the kinetic energy of the protons in the previous analysis. So we expected a lower minus 16.4 electron volts, but we have ended up with a total energy of this system pp equals minus 9.6, which is higher than minus 11.94. But what matters for the ionization is the electrons binding energy term E bind, not this ppe, but what matters is E bind, which is minus 15.4 electron volt. The ppe term can be interpreted as having two components. One, the proton term or the energy associated with the proton part, which is the kinetic energy q by 4 r naught, which in this case turns out to be 5.8 electron volts, and an electron energy part, which is shown as E bind or minus 15.4 electron volts. So we can consider this total energy term ppe to be made up of two parts. One, the proton energy part, which is 5.8 electron volts, and one, the electron binding energy part, which is minus 15.4 electron volts. So adding this 5.8 minus 15.4, we get minus 9.6. Or otherwise, E bind is ppe minus q by 4 r naught. So the black line here shows the curve, graphically shows the whatever we saw the values in the table in the previous slide. This is the graphical representation of the table. So the black line shows the variation of the binding energy E bind as a function of the relaxed separation length r naught. This r naught relaxed separation length 2 r naught normalized by the Bohr radius rb is along the x-axis, and the binding energy is along the y-axis. So as seen from the table and this figure, the minimum binding energy is minus 15.4 electron volts, and the kinetic energy associated with the relaxed length is Q by 4 R naught is 5.76 electron volt or 5.8 electron volt. This implies we have to supply 15.4 electron volts in order to free the electron. But in the process, 5.76 electron volts leaks out as proton kinetic energy. Actually, we are supplying only 15.4 minus 5.8, that is 9.6 electron volt to the electrons. This 9.6 is given by the total energy of the proton-proton electron system, that is pp equals minus 9.6 electron volts. This is all the total energy of the system. But if we supply only 9.6 electron volt to the electrons, it will not get ionized, because we have to account for the extra 5.8 electron volts carried by the protons. So effectively, binding energy is lower than ppe, because we have to negate the kinetic energy carried by the protons. So whenever we supply energy externally, we have to supply not only this 9.6 electron volt to free the electron, we have to supply this 5.8 electron volt extra to the protons so that they can carry this energy out. So that's how the dissociation happens. If we do not supply this, the dissociation won't be complete. So we have to, in order to get the ionization complete, we have to supply 15.4 electron volts, and supplying 9.6 won't do. That is for the electronic transition. Experimentally, it is required that the binding energy be equal to 16.4 electron volt and not 15.4 electron volt as we saw in the previous slide. So if we assume that there is an excess 16% energy loss along with the kinetic energy associated with the relaxed length, that is, we redefine the binding energy E bind as E bind equals ppe minus 1.16 into Q by 4 R naught. Initially in this black line we just used Q by 4 R naught. So in this red line this is multiplied by a factor 1.16. This is 16% extra kinetic energy. So this is the new binding energy. According to the this red line is according to this new binding energy, ppe minus 1.16 Q by 4 R naught. So then we get this red line in the figure if we define the binding energy as this. And the binding energy minima associated with this occurs at 2 R naught equals 2.06 RB. Somehow the experiments are capturing the relaxed length as the bond length and the associated energy as the binding energy. So in this case, the binding energy, the minimum binding energy possible is minus 16.35 electron volts. PPE turns out to be minus 8.67 electron volts, which is higher than the previous analysis. And the kinetic energy of the protons turns out to be 7.68 electron volts, which is also higher than the previous analysis, which is higher than this black line case, what we calculated here using this formula. So this E bind equals minus 16.35 electron volt, and this Q by 4 R naught is 7.68 electron volt. They together imply that this reaction, that is H2 plus, this is the hydrogen molecular ion. If we supply it with 16.35 electron volt, then we get a complete dissociation of it into two protons, H plus and a free electron E minus. And these two protons carry away 3.84 electron volts each. So the summation of these two 3.84 electron volt is nothing but the kinetic energy of the proton, 7.68 shown here. So this is the kinetic energy of the protons in the Coulomb explosion, and we have to supply 16.35 electron volt to get this dissociation, get the dissociation of this H2 plus molecular ion. So after this first step, now a proton and the electron from this end product here, they can combine together and release 13.6 electron volt. So let us assume this H plus 3.84 electron volt associated with this H plus has been lost. This kinetic energy is lost, and simple H plus and E minus react together, combine together. So H plus and E minus gives rise to one hydrogen atom, free hydrogen atom, plus 13.6 electron volt energy is radiated out by the electron. So this is the second step. So in the first step we get this dissociated H plus and E minus, and in the second step one of these proton can combine with the electron to give a hydrogen atom and simultaneously release 13.6 electron volts. So in effect, we have supplied a total energy of 16.35, which we supplied in the first step, minus 13.6, which was released from the system in the second step. We got this back. So the total energy supplied is 16.35 minus 13.6, which is 2.75 electron volt. So we supplied 2.75 electron volts to the hydrogen molecular ion, and we got a hydrogen atom and a proton as the output. That is, the overall reaction can be shown as this: H2 plus 2.75 electron volt is equal to H, which is the hydrogen atom, plus H plus, which is the proton or hydrogen nucleus. So the calculated electronic binding energy of H2 plus with respect to hydrogen atom H is 2.75 electron volt here. 2.75 electron volt, lower than the ionization energy of the hydrogen, which is 13.6 electron volt. So this is minus 16.35. It is lower than the minus 13.6 electron volts of the hydrogen. And 2.75 electron volt is close to the experimental value 2.8 electron volts. The predicted relaxed bond length 2R0 is equal to 2Rb. So this is what we find in the experiment, that 2R0 separation length is nearly twice the Bohr radius. This is close to the experimental value of separation length. So we actually find 2.06 Rb, and experimentally it has been found to be 2 Rb. So this is pretty close. So this is the first main claim we made about ionization energy. That is, this ionization energy is 2.8 electron volts, and also we get the separation length close to the experimental separation length 2 Rb. So this is the first claim made, and we have explained the claim. However, if we add the kinetic energy associated with protons, that is these 3.84 we had ignored this 3.84 electron volts associated with the protons. If we take that into consideration, then we see that we get an excess energy out of this system. That is, we get 13.6 minus 8.67, that is 4.93 electron volts out when the hydrogen molecular ion H2 plus is converted to hydrogen. So basically it is like H2 plus has the total energy minus 8.67. So it is at a higher energy level compared to the hydrogen atom, which has minus 13.6 electron volt for ionization. So in comparison, so if it goes from this minus 8.67 electron volts to 13.67 electron volt, it has to lose this 4.93 electron volt out to the system. But this is not observed. This does not happen. The energy carried by protons is in a different form than the energy due to electronic transitions. So a single type of detector may not be enough to detect the complete energy changes in this process. If we detect only electronic transition energies, then we find that H2 plus, that is the hydrogen molecular ion, has about 2.8 electron volts lower than the ionization energy of the hydrogen atom. But if we consider the proton energies as well, then H2 plus has about 4.9 electron volt higher than the ionization energy of the atom. The radiation based measurements mainly capture the electronic transitions. So that is why we think the H2 plus is at a state 2.8 electron volt lower than the ionization energy of atom. But it is only the binding energy of the electron which is lower. The overall energy of this H2 plus is higher, but the electronic binding energy is lower than the hydrogen atom. So that is the actual case. So let us now consider the net energy equation of the hydrogen molecule, that is H2, with 2 protons and 2 electrons. So this is the energy equation corresponding to this system, H2 molecule. So this is the energy of the 2 proton-proton system we saw earlier, and this is the energy of the electron. So here it is modified. This Q by 2x is a new term, which is the potential energy between the electron and electron. And the kinetic energy of the electron has a factor 2 because there are now 2 electrons. And the potential energy of the electron with protons, it was earlier 2q by square root of r square by x square. It has become 4q by square root of r square by x square. So this entire terms inside this blue square is the energy of the electron, and this is inside this green square is the energy of the proton-proton system. So we can define the binding energy as the total energy minus the kinetic energy of the protons, PPE. PPE is nothing but sum of the EPP and ELEC, which is the sum of the proton energy and electron energy. PPE is the sum of the 2 proton 2 electron system, and binding energy is PPE minus Q by 4R0. But this equation does not give the desired solution, so we shall not discuss this equation here now. But we can define the binding energy as shown here. So we can define binding energy as PPE, that is the total energy of the 4 particle system, minus 1.3 Q by 4R0. That is, this equation has 30% excess energy loss along with the kinetic energy of the proton. So here it is just Q by 4R0. Here it is 1.3, that is 30% higher. 1.3 into Q by 4R0. And this equation gives solution close to the experimental observation. So following the usual method of considering the partial derivatives of E with x and r and setting d square x by dt square and d square r by dt square equals 0, following the usual procedure, we get these relationship between x and r and the ratio r by x. So this is what we get for x. This is the value of x. Given any r by x value, we can find the value of x. And this is the new relationship between the mp omega square and the values of r and x. And this is the old formula that we used. This is from the circular orbit criteria. We use this to find out the relaxed length corresponding to this angular velocity omega. So compiling the table using these expressions and the definitions of E bind and PPE that we defined earlier in the previous slide, we get these values. The minimum energy, binding energy corresponding to this system, this 4 particle system, is minus 38 electron volts, and the total energy of this 4 particle system PPE is minus 24.25 electron volts. So this is shown here by the red line here. E bind equals PPE minus 1.3 Q by 4 or not, which is this red line. So the energy dissipated when the hydrogen molecule with two hydrogen atoms bonded together is converted to two individual hydrogen atoms. That is, when the molecule is converted to individual atoms, the energy dissipated in that process, according to this calculation, is 38 minus 13.6 into 2. So 13.6 comes from the individual hydrogen atom. Since there are two hydrogen atoms, it is 13.6 into 2. So 38 minus this quantity is 10.8 electron volts. So this is the energy that will be dissipated when a hydrogen molecule is converted to hydrogen atom, according to this equation, this expression. But this is too high, and this happens when the hydrogen molecule first dissociates into two individual protons and two individual electrons. That is complete dissociation. That is, H2 becomes H plus, E minus, is broken down into its bare protons and electrons. So if this happens in the first step, that is this process shown here, H2 is supplied with 38 electron volts because E bind is minus 38. When H2 molecule is supplied with 38 electron volts, it gets split into its bare protons and neutrons, individual components, H plus. We get two H plus and two E minus, two free electrons. And these protons are carrying away a kinetic energy of 6.87 electron volt each. And these 6.87 into 2, it adds up to the kinetic energy of these two terms adds up to 13.74, which is given by this 1.3 Q by 4 or not. This is the total kinetic energy of the protons in the Coulomb explosion. So if we ignore the kinetic energy of the protons carried away by the protons, that is the H plus ions, it is like we get two pairs of free protons and free electrons by supplying 38 electron volts to the hydrogen molecule. That is the complete dissociated state. This is in the first step. Then in the second step, one pair of proton electron can combine or bond together to form one free hydrogen atom. So there are two pairs of protons and electrons that were released. Each pair can combine together to form a free hydrogen atom, and the electrons release 13.6 electron volt of energy in this process when they bond. Again, we assume that the H plus has lost its kinetic energy. Whatever the kinetic energy was carrying during the Coulomb explosion, we assume that it has lost it. So this one proton and one electron, they combine together, and another pair combines together. So they produce two hydrogen atom, and they simultaneously release 13.6 electron volts each. So in effect, we supplied 38 electron volts in the first step to get two free electrons out, and these two free electrons release 13.6 into 2, that is total of 27.2 electron volts in the second step, when they combine together with the free protons to form the hydrogen atom. So in this step, this is the second step, we get back 27.2 electron volts from the system. And in the first step, in order to get these free electrons and protons, we had supplied 38 electron volts. So overall, the difference between the input and the output energy per reaction, per such reaction, is 38 minus 13.6 into 2, which is 10.8 electron volts, as noted earlier. In total, the reaction can be written as a two-stage process. In the first stage, this H2 molecule is converted into is completely dissociated form, H plus E minus, two protons and two electrons. And in the next stage, these individual protons and electrons are converted into hydrogen atoms, two hydrogen atoms, H plus H. So this is a two-stage process. But this may not be the most likely process. Experimentally, observed value is 4.4 to 4.8 electron volts, not 10.8 electron volt as calculated here. So this is what we expect experimentally. H2 plus 4.4 to 4.8 electron volt. If we supply this much energy to the hydrogen molecule, we expect to get 2 free hydrogen atom, H plus H. The most likely process may be a 3-stage process like this shown here. First, the H2 molecule will be ionized into H2 molecular ion, H2 plus, and a free electron. Then this hydrogen molecular ion will be dissociated. So it becomes H plus E minus, and this E minus is already there. So it reaches the completely dissociated state in the second step. And then two pairwise they combine together, one proton and one electron, to produce the 2 free hydrogen atoms. So this is a 3-stage process. This may be the most likely process that happens. So that is the H2 molecule in minus 24.25 electron volt state. That is here. So here PPE is minus 24.25, corresponding to the hydrogen molecule. This is the state or the total energy of this hydrogen molecule. When this hydrogen molecule state first ionizes to H2 plus, the molecular ion state, which has a total energy of 8.67 electron volt, producing a free electron. This happens in the first step. It produces a free electron by ionizing. So H2, if we supply it with 15.58 electron volts, it becomes a hydrogen molecular ion H2 plus and releases a free electron. So this 15.58, so note that PPE is 24.25 electron volts, and PPE, the total energy of the 3-particle system, proton, electron, is minus 8.67 electron volts. Therefore, PPE minus PPE is 15.58 electron volts. So this is what we see here in this reaction. So if we supply this 15.58 electron volts to the hydrogen molecule, we can ionize it and get a hydrogen molecular ion and one free electron out. According to Cheng, Hussells, New, Bethlehem et al., published in PRL in July 2018, this ionization value is 15.42. What we measured as 15.58, they have experimentally measured it as 15.42 electron volt, or 124,357.238 per centimeter. They have measured it spectroscopically. So this is the value they get. So the H2 plus in the second step. So this is the first step. In the first step, this happens. We supply 15.58 electron volts to the hydrogen molecule to get one hydrogen molecular ion and one free electron. In the second step, this H2 plus ion dissociates into H plus and E minus in its most dissociated form. This happens in the second step. That is, to this hydrogen molecular ion, if we supply 16.35 electron volt as seen here, this is the binding energy of the H2 plus shown in this table. So when we supply 16.35 electron volt to this hydrogen molecular ion, we get 2 protons out and 1 free electron out. It is completely dissociated state, and the protons carry these 3.84 electron volts each. We saw this reaction earlier. It's the same reaction. So this happens in the first step. We supply 15.5 electron volts, and in the second step we supply 16.35 electron volt to get this completely dissociated state. So the total energy invested in these above 2 steps is 15.58 plus 16.35, which is nothing but 31.93 electron volts. So we have supplied total 31.93 electron volts in these 2 steps. Ignoring the kinetic energy of the protons, the total energy released when the 2 protons and the 2 electrons bond together, which is by forming the hydrogen atom, free hydrogen atom, is this. So here after the 2 steps we will be left with 2 free protons and 2 free electrons. So they can bond together, producing these 2 hydrogen atoms and releasing this 13.6 electron volts. So ignoring the kinetic energy of the protons, these 3.84 electron volts, ignoring that, The difference between the energy input and the output is 31.93, which was the input energy, minus 13.6 into 2, which was released when the hydrogen atoms were formed. So the total energy we input is 31.93 minus 13.6 into 2. This turns out to be 4.73 electron volts. So the overall energy equation, these three steps, if we add up these three steps, we can write the overall final equation as this in a single step. That is H2 molecule, the hydrogen molecule. If we supply it with 4.73 electron volts, we get 2 free hydrogen atoms. So this is the summary of these three steps. Experimentally, the separation length is measured to be 1.4 Rb. While in our calculation we saw in the table, previous table, the relaxed length we measure is 2R0 is 1.3 Rb, which is pretty close to the experimentally measured bond length. And also the calculated dissipation energy, which is 4.73 electron volts shown here, is within the range of the experimental measurement. In the experimental measurement, we see a wide range from 4.4 to 4.8 electron volt for this particular reaction. And we are close to the higher end of this, but we are well within the range. So we can explain this 4.73 using the values we have taken, which is pretty close to the experimentally determined value. So we can explain this claim also. So a few slides earlier, we saw the explanation for the experimental observation. H2 plus 2.8 electron volt gives rise to hydrogen atom and a proton, H and H plus. So this is about the dissociation of hydrogen molecular ion. So we can explain that. We explained that in some of the previous slides. The discussion in the last 2-3 slides explains the experimental observation. H2 plus 15.4 electron volts gives rise to H2 plus and E minus, which is nothing but the ionization of the hydrogen molecule. So if we supply 15.4 electron volts, we can ionize the hydrogen molecule. This was noted at the top of this slide, this reaction shown here. So we have explained that also, that claim also. And we also explain H2 plus 4.74 electron volts is H plus H. 4.74 is the value from one of the publications. So if we supply 4.74 electron volts to this hydrogen molecule, we get 2 free hydrogen atoms. So we explained this experimental observation also here. So these three reactions we explained in this video presentation. These three are the experimental observations, and we have explained it theoretically in this presentation. So these are mainly observations about electronic transition. These three reactions are mainly observations about electronic transitions. It seems the experiments mostly ignore the kinetic energy carried away by the protons as Coulomb explosion. This is possibly because this Coulomb explosion is not associated with radiation like electronic transitions. That is, the electronic transitions are associated with radiation. Their measurements will be in a different way than the kinetic energy carried away by the protons. So since we are mainly measuring the electronic transitions, these are the reactions we see. So this is how we explain the three reactions that we see, which are related to the electronic transitions of the hydrogen atom. So we end this presentation here. Thank you. If you want to understand the concepts of physics in the clearest way, regardless of the concerns about scoring high marks in exams, please visit neophysics.com. Thank you.